Hi. So at this point, we can proceed to the practical part with high-resolution image diffusion. As mentioned in the previous episode, we will need an autoencoder module in order to encode our image samples from pixel space to latent space, and then decode back once we have generated something new. So the framework structure will be quite similar, as we will have again, three underlying modules wrapped by a denoising diffusion process, but the lightning module will be changed from pixel diffusion to latent diffusion in order to also contain one more additional component, which is the autoencoder. Okay, and that's about it. Everything else stays basically the same. So for unconditional generation, first, before we do anything, whenever we import a new autoencoder that's supposedly been retrained on a dataset like ImageNet or something else that's relevant for us, something that we hope to work well with our images of interest. We want to check the expected input transform, so whether it expects something between 0 and 1, -1 and 1, or maybe some other type of normalization. And we also want to check the variance and basically the magnitude of the latents in the encodings. So when we encode our images, we want to make sure that they're actually close to -1 and 1 range. So they generally fall within that range, because I don't know if that's been mentioned in the previous episodes, but DDPM and the denoising diffusion processes are generally run on the assumption that the images will be between -1 and +1 range. Which is what we usually do for all the other variants of diffusion and DiffusionFastForward. So if you see that your latents are diverging too much from this range, you can apply some constant scalar factor. That's what's being done in latent diffusion, and that's what we also do for our autoencoder. So what we need to do is change the training step. We still use the same PLOS, so that remains the same, the underlying diffusion mechanism. But instead of diffusing images, we will be diffusing latents. And latents are obtained by encoding our images, by running the appropriate input transform, and then multiplying by a specific latent scale factor that I was referring to earlier. For the forward, it's again quite similar. But once we've produced our latent code, we need to divide by our latent scale factor to go back to the original range of our latent, and then decode and apply the reverse output transformation. For the conditional model, we do something similar, but we also need to provide the condition, and the condition is also encoded using basically in the same way. And we also multiply that in the same scale factor. So basically, it goes through the same process as the normal input. Okay. And for generation, we again need to encode. We need to encode our latent. We need to multiply it by the appropriate factor, and then we can generate with that condition latent, and then proceed as we would normally with unconditional diffusion. Okay. So this is our 256 by 256 version of our MAPS dataset. The samples are in much higher resolution than we used in the earlier examples. And these are examples of our input. And we essentially want something that will resemble aerial images that correspond to these maps. And after training for again, in Colab for about, I think, 12 hours, if I remember correctly. You can check the details on the README of the diffusion course. You can get these types of samples, okay? But in general, it will take a bit longer, no matter what, to generate images in high resolution. Obviously, there's still some work to be done in terms of converging to higher quality data, but it's definitely going in the right direction. Whenever you want to train models, not just for experimentation, but maybe for deployment, you need to be patient and you need to train them for much longer. So at this point, we can check out the latent diffusion notebooks. The latent diffusion notebooks are linked here. It's notebook 4 and notebook 5. and they correspond to unconditional and conditional latent diffusion. In this case, again, conditional is image-to-image translation mode. And everything else stays the same, really, apart from the fact that we will be using 256 by 256 images. And I don't know if we have results here. The results will be in the README, so this notebook hasn't been run, but you run it in the exact same way as you would the other notebooks. And same with the conditional latent diffusion. It's all pretty much the same, but you have these 4 modes of generation to play with. Okay, so that's it for now. This is the last practical episode from this main version of the course. There are some additional episodes that you are free to check out. So there are the extras on diffusion applications, the further insight into diffusion, and if you haven't checked that out yet, there's also a summary of seminal works. At the point of releasing this episode, it might still not be. These extra episodes might still not be out. So hopefully, if you subscribe and follow the course, you will be able to access those as soon as they are published. Okay. Thank you for now.